Welcome back to Astronomy. This is Chapter 20, Galaxies, and the Foundation of Modern Cosmology. This video is Part 1, Introduction to Galaxies. This is a picture from the Hubble telescope, and all of these are galaxies, and you can see the variety of colors, you can see the variety of shapes. All of these are things like the Milky Way galaxy that are way beyond the Milky Way. When we study galaxies, it brings us to the study of cosmology. Cosmology is the science of the origin and development of the universe. You can think of it as the study of the big picture of the universe, the large-scale structure of the universe. A little bit of Greek here to practice the Greek letters you've been learning. Cosmology actually comes from two Greek words, kosmos and logos. And cosmos in the Greek can mean world or order. And logos means word. And often we add logi on the end to words like biology, zoology, otorhinolaryngology, to mean the study of. So this is the study of the order of the world, and actually not world meaning earth, but meaning the universe. Hopefully you remember a lot of these Greek letters. Here is kappa, omicron, sigma, mu, omicron. And this letter here is also sigma, but not the sigma that you learn in astronomy class. It's a different sigma. It's the sigma that the Greeks put on the end of a word. It's actually called final sigma, but that word is cosmos. And then this word logos, lambda, omicron, gamma, omicron, and then the final sigma again. So cosmology, the study of the entire universe. This picture from the Hubble Extreme Deep Field, the HXDF. Our deepest images of the universe show a great variety of galaxies, some of them billions of light years away. Now you see this picture here, and next to it a thumb with a little dot on the thumbnail. What this represents is that picture is a very, very small portion of the sky. In fact, it's such a small portion, if you hold your hand out at arm's length, then that little dot shown on the thumbnail, that is the size of that picture of the sky that it's taking. So Hubble was pointed in a direction, not pointing at any stars, in fact, a pretty empty spot in the sky where it just looks black to our eyes. And even with a normal ground-based telescope, it looked pretty black. And Hubble was pointed in that direction and found all these things, all these galaxies out there. And there was nothing particularly special about that direction of the sky it was looking in. It turns out that any direction that Hubble looks, looking outside of our galaxy, shows this vast variety of galaxies. The astronomers think that there are roughly 1 trillion galaxies in the universe. A galaxy's age, its distance from us, and the age of the universe are all closely related. The study of galaxies is thus intimately connected with cosmology, which is the study of the structure and evolution of the universe. So as we study galaxies, we are learning not just about those galaxies themselves, but we're learning about the universe as a whole. And we'll explore that in this chapter. So what patterns do we find among the properties of galaxies? In this picture, you see 3 different spiral galaxies. There are other shapes of galaxies, but these are galaxies that are similar to the Milky Way. You've already learned in Chapter 19 that the Milky Way is a spiral galaxy. But let's look at other types of galaxies. We divide galaxies into 3 major categories based on their shapes. And those categories are spiral, elliptical, and irregular. We'll look at spiral galaxies first. You've already learned about the Milky Way and its spiral shape, so look at these 3 galaxies. The one on the left is facing us directly, face on, so we can look perpendicular to its axis of rotation. And we see the central bulge, we see the disk, we see those spiral arms. The one on the right, we are looking edge on at it, so the central bulge with the disk. And you notice there's this dark line going through it, and that is the dust that is settled in the center of the galaxy, much like with the Milky Way. And the picture in the middle is a bit tilted to our line of sight. So both of these are good pictures that show us the structure of a spiral galaxy. Just as with the Milky Way, notice if you've got your central bulge, you've got your disk with the spiral arms, and you've got your halo surrounding it. Here, the central bulge, part of the halo or spheroidal component of a spiral galaxy, can be seen prominently. And again, this is a very nice picture because you can see the dust that is blocking out the light from the disk of the galaxy. This is the Whirlpool galaxy. Good, beautiful picture because we are looking perpendicular to the axis of rotation, looking down on the spiral. But notice it's got a little companion galaxy off here to the left. It's got a miniature spiral galaxy next to it. I want you to see the different colors in this picture. The spiral arms have a lot of blue in them, and blue is an indicator that there's a lot of active star formation going on because blue stars don't live very long. So you're seeing stars that must be young, and there's a lot of them, a lot of star formation in those spiral arms. Notice as you get towards the center, it's not dominated by blue. It's dominated by more reddish and yellow. So when you see in a picture of a galaxy regions that are particularly red, orange, and yellow, then that's showing more of a population of older stars and not as much star formation going on. This is a barred spiral galaxy. The young bluish-white stars associated with ongoing star formation in the disk can be seen. You can see, hopefully, why it's called a barred spiral galaxy. Notice that the spiral arms, the spirals do not start directly from the central bulge, but rather there's the bulge and then what looks like a bar, and then the spiral arms come from it. And that's actually the type of galaxy that the Milky Way is, not just a spiral galaxy, but a barred spiral galaxy. A lenticular galaxy is a type of spiral galaxy. It's actually on the border between spirals and another type called ellipticals. It looks like an elongated football. Lenticular actually means like a lens. It's shaped like a convex lens. It has a disk like a spiral galaxy, but much less dusty gas. And as I said, it's intermediate between a spiral and an elliptical galaxy, but it's still considered in the category of spiral galaxy. Now that brings us to the next type of galaxy, an elliptical galaxy. Picture a spiral galaxy, but with no disk at all, just the central bulge with the halo around it. So it's all the spheroidal component that a disk galaxy has, and no or virtually no disk component. These typically have older star populations, not as much gas and dust in them for active star formation. The red-yellow color indicates an older star population. This particular galaxy in this picture is a giant elliptical. It's called M87. It's about 55 million light years away. It's one of the most massive galaxies in the universe. This large galaxy is the Andromeda Galaxy. You can see it's a spiral galaxy. Notice the central bulge with the more yellowish color. Notice the disk with the spiral arms with the blue, the more active star formation. So it's a spiral galaxy. It has a little companion down here and to the right. That galaxy is an elliptical. Let me zoom in on it. So there it is, the elliptical galaxy that is in orbit with the Andromeda Galaxy. An elliptical galaxy is a ball, although it could be an elongated ball, so pushing like an egg or a football, or it could be a sphere. The third type of galaxy has no classifiable shape, no symmetry. This is the everything else category, and they're just called irregular galaxies. So if it's not a spiral galaxy with the nice disk, or it's not an elliptical that's a ball, it's just a blob of stars and gas, then we just call it an irregular galaxy. Notice in this picture of the Large Magellanic Cloud, there's a lot of blue, so the blue-white color indicates ongoing star formation. The Large Magellanic Cloud is a companion to the Milky Way. It's about 30,000 light years across. And remember, in comparison, the Milky Way's disk is about 100,000 light years across. This is a picture in the sky. Notice the tree line down below. So this was not taken with a telescope, of the Large and Small Magellanic Clouds. And if you're wondering, why have I never seen that in the sky? Well, it's a southern hemisphere thing, so you have to be in the south to see it. But on the right is the Large Magellanic Cloud, and on the left is the Small Magellanic Cloud. Edwin Hubble, who discovered that many of these objects out there in space that they had thought were nebulae are actually galaxies. So he discovered that there are other galaxies. He started classifying galaxies, coming up with these classifications of ellipticals and irregulars and spirals. And he came up with what's known as Hubble's tuning fork diagram. And you can see these different types. So let's actually start on the right. We have a variety of spiral galaxies. Now, let's go to the top. It says SA, the capital S stands for spiral, SB and SC. The A, B, and C refer to the size of the central bulge relative to the disk. So he called spiral A galaxies ones with a fairly large central bulge compared to the disk. B is kind of medium size, and C is a small bulge compared to the disk. Now, he also recognized that there are barred spirals. So let's go down here, and capital S, capital B means spiral barred, and then the lowercase ABC again refers to the size of the bulge relative to the disk. So SBA, SBB, and SBC. And the Milky Way galaxy is actually classified as an SBB. So about a middle-sized bulge compared to the disk, spiral barred. Notice as we go from right to left, larger bulge has less dusty gas and tighter spiral arms. Now, this is not an evolution chart, meaning galaxies do not start on one end and go to the other. Just like with stars, the main sequence, stars do not travel up and down the main sequence, but rather the initial conditions of a galaxy and sometimes interactions with other galaxies will determine what type it is. Now, we go to a relatively larger bulge, and we get these S0s, and these are lenticular galaxies that have a bulge very large compared to the disk. In fact, the disk, there isn't really much of a disk that comes from the bulge. And then we can have SB0. So these are lenticular galaxies right here. And as I said earlier in this video, lenticular galaxies are the crossover between spirals and ellipticals. So now we get into ellipticals, which are just think of it as the sphere components, the central bulge and halo components of a otherwise spiral galaxy. And they go from E0 to E9. On this chart, they've only drawn E0 and E5, but they go from 0 to 9. E9 is just a very elongated, like a football. And then as the number goes down towards 0, it gets more and more spherical, more rounder. So an E0 galaxy would be a fairly spherical elliptical galaxy. Irregular galaxies do not appear on this tuning fork diagram. Spiral galaxies are often found in groups of galaxies. Remembering back to chapter 1, when you first learned about the different large structures in space, you learned that there are star systems that are a part of galaxies. Galaxies are in either clusters or groups. And in chapter 1, I didn't get into the nuances between a cluster or a group of galaxies, but a group of galaxies is what we call it when there are just a few dozen. So a group is like a small cluster. And spirals tend to be found in groups of galaxies. Elliptical galaxies are much more common in clusters of galaxies. So a cluster is just a very large group. Clusters can be hundreds or thousands of galaxies. Let's talk about the local group. You learned in chapter 1 that we are in the solar system, which is in the Milky Way galaxy, which is in the local group. That is our group or cluster, small cluster, of galaxies. Let's talk about the local group. The Milky Way galaxy is in the local group, which contains 47 known galaxies. Now, every now and then, we discover a new galaxy, even in our own group, but currently the number is at 47 that we know about. 3 spiral galaxies, the Milky Way and the Andromeda being 2 of them. We are the dominant galaxies in the group. There are 24 elliptical galaxies, although 22 of those are what's called dwarf elliptical galaxies, so just small ellipticals. And then there are 20 irregular galaxies, bringing the count up to 47. Thinking about the scale and the layout of the local group, from the Milky Way, those other galaxies are distances between 25,000 light years and 5.2 million light years away. Now think about what that means. A galaxy 25,000 light years from us. The size of the Milky Way is 100,000 light years. So there are a few galaxies that are closer to us than the size of the Milky Way. So they are actually merging into the Milky Way, becoming a part of the Milky Way. If you want to do a scale model of the local group, you can take something about the size of a softball to represent the Milky Way, and a slightly larger ball would be the Andromeda galaxy. Then our local group consists of 47 such objects. Again, the Milky Way and the Andromeda would be the largest ones, so use smaller objects, and they would all be within about 10 meters of each other. So they could fit, our local group on this scale could be 47 of these balls around the astronomy classroom at the college. That is the end of part 1, the introduction to galaxies. Have a great day.